The views expressed on Skeptically Speaking are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Bring it on! The skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Shell gonna raise a little hell, metaphorically that is. 'Cause we're skeptically speaking.
Hello and welcome to Skeptically Speaking. I'm your host, Desiree Shell. I'm here with James Kakalios, the Taylor Distinguished Professor in the University of Minnesota's School of Physics and Astronomy. His popular science book, The Physics of Superheroes, was published in 2005, and it's been translated into German, Spanish, Korean, and Italian. His new book, The Amazing Story of Quantum Mechanics, was released in 2010, with the paperback coming out in November of this year. And although his research interests currently include things like nanocrystalline and amorphous semiconductors and fluctuation phenomena in neurological systems, he's been reading comic books longer than he's been studying physics. Welcome to Skeptically Speaking, Jim.
Oh, thank you very much, Desiree. Thank you for having me.
Now, your book intersperses the progress of quantum physics as a discipline with the evolution of science fiction. Mm-hmm. So why present it that way?
Well, there's an interesting historical fact that the very first science fiction pulp magazine, Amazing Stories, devoted exclusively to science fiction, begins publication in April 1926. Also publishing in winter of 1926, Erwin Schrödinger, publishing his paper on the Schrödinger equation, which basically starts modern quantum mechanics. So these two visions of the future branch off at nearly the same point. But it really started with a question that scientists get asked often enough. Here we are in the 21st century. We were promised jetpacks and flying cars. Where are they? And my answer is we didn't get the jetpacks or the flying cars, but what we got instead were cell phones and laptop computers. And a lot of this, when I trace back why, in order to have a jetpack or a flying car, in order to lift a car up off the ground, requires a tremendous amount of energy to constantly counteract gravity. Whereas computers, cell phones, a lot of technological devices really involve manipulations in information. So the pulps, the science fiction pulps and comic books thought that we'd have a revolution in energy that would make things like jetpacks possible, where what we got instead was a revolution in information. That information revolution came about thanks to semiconductor and solid-state physics, which in turn was enabled by the discovery of quantum mechanics.
Well, there seem to be a lot of examples of science fiction authors writing about technology that wouldn't be possible for years. And while we don't have time machines yet, nor jetpacks, Jules Verne did predict things like the fax machine. So did science fiction writers just have fantastic imaginations, or were they actually consulting the available science?
Verne is a very interesting case in that he basically did what you would expect to do for a real scientist. He looked at what the state of the art was, and then he extrapolated out a little bit. So he made small excursions from the shore, but he was in a very interesting point in history where technology was really coming into its own. And so his extrapolations would lead to things like submarines or heavier than air aircraft that could fly, and that turned out to be correct. Nowadays, there's even, people are still occasionally getting their predictions right. Science fiction author Neil Stephenson, in a novel back in the mid-1990s called The Diamond Age, predicted that there would be these smart books, basically electronic paper that you would fold it open. It would pick up the radio signals that surrounded you, and it would display, say, a newspaper page. And then you would touch a button and you go inside the story. And this was on a flexible sheet of paper. The only thing we don't have right now is that it's on a flexible sheet. But with organic semiconductors coming along in line, that might actually come into play as well. So he predicted smart books. He predicted things like basically the iPad, all back in the 90s. So there are still cases of science fiction writers who can have their finger on it and can get things right. But a lot of it, of course, involves cherry picking. We'll look at those cases where they get things right and completely ignore those cases where they blow it completely. It's kind of like the argument about how come so much classical music is so good. Well, there was a lot of classical music. The stuff that survived, several hundred years is the great stuff. The junk, we don't hear anymore. So I suspect in some cases, some of these writers look very prescient simply because those are the ones that actually managed to make the leap.
Well, you say that the writers expected a revolution in energy, but what they got was a revolution in information. So how would the world be different if it would have gone the other way?
In many different ways. There'd be positive aspects. If you had a energy supply that you could wear on your back that would power you for an extended ride as a jetpack. I mean, we do have jetpacks today. You could take a jetpack to work, provided that you only lived a few blocks from where you worked, because it takes a lot of energy to lift you up off the ground. And when you're done with that, you can only have a ride of a few minutes in length. With conventional chemical fuels, if you're willing to have an unlicensed nuclear power pack on your back, either you're very foolhardy or a member of the Ghostbusters. But what would it be like? Well, if we had these portable energy supplies, forget about jetpacks and transportation. We'd be able to use them to desalinate water and provide fresh, safe drinking water to large portions of the global population that don't have access to potable water. So that would be a consequence that we would not have seen. Another consequence, if we didn't have that revolution in information, we'd still have computers, but instead of transistors, they'd have to use vacuum tubes in order to perform the same tasks. And so if you wanted a large, powerful computer, you'd need a large number of vacuum tubes. You'd need a large room because these vacuum tubes are fairly large in size. They generate a lot of heat. They're bulky. And so powerful computers, a few corporations and the government would have it, but there wouldn't be a big, powerful computer in everyone's house.
Right.
Consequently, there'd be no reason to link them together in an internet, and so no World Wide Web.
That is horrible, sir.
I am second to no one in my desire of a jetpack, but if you were to tell me jetpacks or the World Wide Web, I think I'd go with the web.
I think everyone will agree that listens to this show.
On the web.
How much of that revolution then was due to quantum physics? Is it the majority of it?
I would say a fair amount of it. Solid-state physics, semiconductor physics, at its heart, is basically applications of electromagnetic theory, which were developed for the most part around the time of the American Civil War by James Clerk Maxwell in the 1860s, and quantum mechanics. Without quantum mechanics, you really don't have a fundamental understanding of semiconductors and how to change their electronic properties by the addition of a small amount of chemical impurities. Without that control, you won't have diodes, you won't have transistors. And so a lot of the basic building blocks of the technology that we take for granted really requires an understanding of quantum mechanics. It's not enough. Just having quantum mechanics, just having electromagnetism doesn't get you a semiconductor device, doesn't get you an integrated circuit, but it may not be sufficient, but it's certainly necessary.
Now, what you've tried to do with your book is sort of, I believe you used the term a working man's perspective on quantum physics. And you also say that quantum physics is just like other physics, although it does have a reputation for being far more bizarre and confusing. So why is that?
Well, my idea of the working man's view is quantum mechanics, as you say, has this reputation for involving these weird, outlandish ideas. And certainly the ideas that underlie quantum mechanics are indeed weird. But one of the most amazing things about quantum mechanics is how useful it is. Without quantum mechanics, you would not have lasers. And without lasers, you don't have CDs and DVDs. You don't have, a tremendous amount of technology. Again, without quantum mechanics, you don't have transistors. So it's an extremely useful branch of physics in addition to everything else. Now, when I say that it's not that unique as part of physics, classical electromagnetic theory, which, as I said, has been around since the 1860s. The fact that we live in a sea of electromagnetic waves that, except for a very narrow slice in the frequency spectrum, we are completely unable to detect. We never think about this really strange idea unless we can't get a cell phone signal.
Right.
And then suddenly you only notice it when it's not there. Similarly, in the early days of electricity, people were very afraid of electricity. They thought it was a very strange thing. Some people didn't want to touch an electric doorbell button because they were afraid that somehow the electricity was going to come through the button and kill them. We've had over 100 years to get used to these ideas. So in my book, I present some of the key ideas that one needs to understand quantum mechanics in order to understand how a laser works, in order to understand how magnetic resonance imaging works, that type of thing. And we build on this, and hopefully in some period of time, these ideas won't be so strange and bizarre, and people will have accepted that as much as they've accepted things like electromagnetism.
We have a question from the chat from Gravespinner.
James, can you give us your definition of quantum physics?
Quantum physics is that branch of physics that deals with the properties of atoms and how they interact with light. One of the weird ideas of quantum mechanics, which has been experimentally verified over and over again, is that with the motion of all matter, there is associated with that motion a wave. And it's not an electromagnetic wave, but there is a wave-like property to the motion of all matter. The larger the momentum, the smaller the wavelength. They vary inversely. Now, we don't notice this because for a person walking across the room or, a baseball thrown from the pitcher to the catcher, the momentum is fairly large because it contains a large number of atoms. So the wavelength is smaller than trillions of times smaller than a nucleus of a single atom. So there's no way to ever detect that. But for an electron weighs a lot less than a baseball. And for an electron inside an atom, its momentum is such that its wavelength is about the size of the atom. So while it's impossible to detect the waves of macroscopic objects like baseballs or automobiles, for electrons inside atoms, it's impossible to ignore. And this wave-like property associated with all matter, which becomes dominant when you get down to the length scale of atoms, governs the properties of atoms, governs how they interact with light. And quantum mechanics is the branch of physics that tries to understand what those rules are for how the electrons and their wave-like properties and light and its particle-like properties interact with each other and give rise to the observations that we have of the world around us.
That was kind of beautiful.
Well, it's quantum mechanics that's beautiful.
You're listening to Skeptically Speaking, and I'm talking with Professor James Kakalios about his book, The Amazing Story of Quantum Mechanics, a math-free exploration of the science that made our world. Now, there has been quite a bit of disagreement within the field, and there still is on certain points, but in the past, it was even about the basics. When Einstein suggested that light was comprised of discrete packets of energy, the idea wasn't exactly welcomed with open arms.
No, absolutely. And in fact, the person who first began quantum mechanics, Max Planck, made a very minimalist hypothesis about quantization of energy, that energy could only be lost by atoms in discrete packets in order to account for the observed spectrum of light given off by all hot glowing objects. No, these scientists, they were not introducing these weird ideas because they were weird. They were not introducing them to be provocative. They were faced with a set of observations of nature that were fairly universal, that conventional electromagnetic theory, conventional thermodynamics was completely unable to predict. The conventional theories at the time made actual specific predictions that were in complete contradiction to what was observed. And so there was a problem. And so these ideas were introduced a little bit at a time. They were resisted by a great many scientists. In some cases, they were even resisted by the scientists who introduced them. I mentioned Erwin Schrödinger earlier, whose Schrödinger equation is considered one of the foundation points of modern quantum mechanics. He completely misinterpreted his own equation. He came up with this equation that describes the properties of atoms, and he thought that if you take this quantity that the equation solves for, the wave function, and square it, that it would give you the charge density inside the atom. A year later, Max Born said, no, it's not the charge density, it's the probability density. It's the probability of finding the electron at some point in space and time. Born's interpretation of the Schrödinger equation is viewed today as the correct one, whereas Schrödinger resisted this for most of his life. And he did not like this whole notion of probabilities. And the famous Schrödinger cat thought experiment was actually introduced by Schrödinger to point out how silly he thought this probability interpretation was. This is kind of an interesting thing where the mathematics is there, and you can make predictions from the mathematics, and you can compare these predictions with experiments, and they agree perfectly. But in terms of trying to understand things in our conventional way, trying to understand, like, well, what is the electron really doing? That stuff is the stuff that leads to late night discussion sections in college dorms. In some sense, quantum mechanics is an amazing, almost perfect physics theory because it makes accurate and reliable predictions for any measurement that I, as an experimentalist, might care to make. And for those things that I can't measure, that's where it gives all the philosophical mumbo-jumbo. But if I can't measure it, what do I care? There's actually a school of thought in quantum mechanics that's called shut up and calculate. That literally, this is like there's like a school of thought about quantum mechanics that says, yeah, what is the electron doing? I don't care what it's doing. I just want to figure out, how do I make this device, and how do I make sure it works? How do I understand this radioactive decay? How do I can I predict the lifetime of this radioactive isotope? And quantum mechanics, if you just shut up and calculate, will give you answers that you need. And this is the sense where my book provides a working man's view of quantum mechanics. I don't get into the philosophy. I don't get into, issues of the measurement problem. I think I've written one of the only books about quantum mechanics that doesn't discuss Schrodinger's cat. But I also wrote a book about quantum mechanics that explains how magnetic resonance imaging devices work. And that's all quantum mechanics. It's a completely quantum mechanical phenomena from soup to nuts. And so I explained the basics of that. The quantum mechanics of your computer hard drive. The difference between CDs, DVDs, and Blu-rays. And so there's a lot that's all around us. Without quantum mechanics, you wouldn't even have a solid-state television remote control. And to the men who are listening right now, you're welcome.
Well, that's actually one of the things that your book did. It hurt my head considerably less than many other physics books, so thank you, because you used a lot of metaphors, which I appreciate. But
yes.
you also looked at it through the lens of science fiction. So let's start with John Osterman.
John Osterman was a physics professor in a very famous comic book miniseries, Watchmen, that came out in the mid-1980s, written by Alan Moore and drawn by Dave Gibbons. And in Watchmen, they posit a world where there are superheroes, where people dress up in costumes and go out and fight crime. But for the most part, aside from having a few technological devices, these are non-superpowered individuals, except for John Osterman, who is caught in a physics experiment that's gone awry, as they inevitably do, and has what is called his intrinsic field removed. And the intrinsic field is, in the comic book, as is explained, is supposed to be everything except gravity. Well, there are four fundamental forces of nature: electromagnetism that holds atoms together, the strong force that holds nuclei together, the weak force that is involved in some certain forms of nuclear radioactive decay. But if you were to turn off the electromagnetic force, there would be nothing to hold your atoms together. If you were to turn off the strong force, nothing would hold your nuclei together. And so you would be taken apart at the subatomic level. Through a process that remains poorly understood to this day, John Osterman was able to reassemble himself by pure force of will. In so doing, he gained a set of amazing superpowers, and as a public relations move, the government gave him the code name Dr. Manhattan. Initially, he fought crime, he worked on the side of the government, but then eventually he started to become an independent agent. But in terms of trying to understand John Osterman's powers, it's kind of fun to look at this, and this is the same process that I did in Physics of Superheroes, and said, well, what impossible thing do I have to accept in order to account for this character? And it turns out that an awful lot of his powers could possibly be justified if you were to say that he gains independent control of his quantum mechanical wave function. So that I mentioned that every object has a wave associated with it, but normally this wave is so small that it's completely undetectable. But if Osterman can control his wave and its spatial extent at will, then he could do various things, like he could make it extend over great distances, and then he could have the wave have a large amplitude at some other location, and he would appear at that other location, so he would basically be teleporting himself. He does this in the comic books, and this would be a correct use of his quantum mechanical powers. The quantum mechanical wave function, if you solve the Schrödinger equation, has all information about the probability of finding an object at some point in space and time in both past, present, and future. And Osterman seems to have awareness of himself, both in his present and his past, but also things that will happen to him in the future he seems to be aware of. He has a blue glow. If you built yourself back together from scratch, you'd probably be leaking high-energy electrons, and that would give off a blue glow like called Cherenkov radiation. And so even his blue glow could be, with some hand-waving, argued for, if not completely justified, by talking about the quantum mechanics behind it. There's a lot of things about that could hold together, but it's not. My job is not trying to explain how Dr. Manhattan's powers work. They clearly don't work, but it's fun to use that as an illustration of different aspects of the quantum mechanical wave function. And then I show how those same aspects of the wave function get exploited when we try to understand atoms, when we try to understand solids, the differences between metals and insulators, and things like that.
Well, since you've brought up Schrödinger a couple of times, we all do know the undead cat story. So let's not talk about that. The problem is, I think without that, very few people know what that means. And even with that, very few people know what that means. So what does Schrödinger's equation explain?
Schrödinger's equation is basically like Newton's second law, but for electrons inside atoms. It basically says, Newton's second law says force is equal to mass times acceleration. You tell me all the net forces acting on an object, such as a baseball that I throw through the air, and the forces might be gravity and air resistance. You tell me the initial conditions, the speed and location where I toss the ball, and I can then predict the future trajectory of the ball. I can answer all sorts of questions. How high will it go? How far will it go? How fast will it be moving when it reaches a certain point? Schrödinger's equation says you tell me all the forces acting on an electron, and I get a quantity from this equation then, not the acceleration, but what's called the wave function. And if I square the wave function, do some mathematical operation to it, it tells me not the future trajectory, but the probability of finding the electron at some point in space and time. So if I know its probability of finding it at any distance from the nucleus, I could calculate, say, its average distance from the nucleus. And when I do a measurement and compare it to that predicted average value, it agrees exactly. It can tell me the probability of it having a certain momentum, or what are the possible energies that this electron could have inside the atom. And when I compare to experiments, perfect agreement. So in some sense, the Schrödinger equation is the quantum analog of Newton's laws. Newton's laws of motion are the underpinning of classical mechanics, whereas Schrödinger's equation, or an alternative formulation of it, the Heisenberg uncertainty principle, are the underpinnings of quantum mechanics.
The Heisenberg uncertainty principle, I think, is really what breaks people's brains.
Absolutely. What the Heisenberg principle really says is it's not saying that I can't measure position and momentum, say, at the same time, nor is it even saying that I can't measure it with a certain number of decimal places. But if I do a measurement and I get the position and I get the momentum of an object, I would like to know that I did it correctly. So maybe I'll repeat the measurement thousands of times. And when I plot up all the measures values that I obtain, I'll get a histogram. I'll get some sort of bell-shaped curve for the position and some sort of bell-shaped curve for the momentum. And the uncertainty principle basically says that the width of the position's bell-shaped curve, that standard deviation that tells me how broad the distribution is, that width is related to the width of the momentum. And I can't make them independently as narrow as I like. And why not? It gets back to that point that I mentioned earlier. Momentum is associated with a wave-like nature. And so the more precisely I know the momentum, the more the electron's motion, or any motion, is described by a perfect wave. And a perfect wave is a wave that just extends out forever. That is one single sine wave. Mathematically, it would just keep going forever. And you would have one wavelength from plus or minus infinity, one wavelength, perfect knowledge of the momentum. But if the electron is described by this wave, and you ask, it goes from minus infinity to plus infinity, where is the position? Then you have perfect ignorance, perfect uncertainty in the location of the electron.
Right.
Or you could do it, turn it around the other way. You could squeeze the electron in a box finer and finer. But in order to describe that by a wave, I have to add more and more different types of waves in order to get them to cancel out outside the narrow location. But the more different waves I add, the more different momenta. So the more precisely I determine the position, the more imprecisely I know the momentum. So the fact that there's a wave-like nature associated with the motion is basically the underpinning that gives you the uncertainty principle, and you can't beat that because that seems to be the way nature is.
Well, and just to clarify, though, this doesn't mean everything is uncertain, although that's the idea that's kind of wormed its way into pop culture.
No, just as much as the Einstein's theory of relativity doesn't mean that everything is relative. But this is part of the problem. Sometimes in science we use terms that are also used in everyday speech. But in science, we're using them in a very precise and narrow way. So when we say uncertainty, mathematically what we are referring to there is the width of those histograms. So instead of saying the uncertainty principle, if Heisenberg had called this the principle of complementary standard deviations, I doubt that people would have tried to base all sorts of, make connections to Eastern mysticism in that way.
Exactly. We have a question from Steve by email.
Could you explain the many worlds theory in a way that does not, as Desiree said, break my brain?
Now I have to break down and I have to talk about Schrodinger's cat. So let me tell you briefly about Schrodinger's thought experiment and Schrodinger's cat. The Schrodinger equation can tell you the probability, say, of a radioactive isotope decay. And say you have a 50-50 chance that the isotope decays in a year. You have 1 million isotopes. You come back a year later, 500,000 sure enough have decayed. The only problem is that you don't know which 500,000 until you've come back in a year. So Schrodinger said, well, I don't like this idea about probabilities. Let me show you how ridiculous I think it is. Say I have one isotope. Say it has a half-life of 1 hour. So after an hour, there's a 50% chance it decays, a 50% chance it doesn't decay. You will tell me that if I try to observe this isotope, I can change its probability of decay. So I will set up an arrangement so that when it decays, it will emit a radioactive particle. That radioactive particle will be detected by a Geiger counter, and the voltage from the Geiger counter will send a signal that will break open a bottle of poison gas and will kill a cat inside a box. You may argue that observing the isotope changes whether it decays or not, but few people would say looking at a cat changes whether it's alive or dead. So after an hour, you open up the box and you see whether the cat is alive or dead. Before you open up the box, the standard interpretation of quantum mechanics says that the only way to describe the cat is at an average of half alive and half dead. That sounds so stupid that scientists use different language and say that it's in a linear superposition of two orthogonal quantum states. And when you open up the box, the wave function collapses into either one observable or the other. But basically you're saying it's half alive, half dead. Physicists didn't find this very satisfactory. In 1957, Hugh Everett III, as part of his PhD thesis at Princeton University, has figured out another way to think about the problem. He says, I'll tell you what happens to the cat in the box. It has nothing to do with it being half alive, half dead. When you close up the box, you split off two parallel universes. And at the end of the hour, you open up the box, and there's no collapsing wave functions. All you do is discover whether you live in the universe where the cat lives or the universe where the cat dies. And for every quantum event for which there's at least two different outcomes, there's that many different parallel Earths. Basically, it's a way of saying to say, if there's a 90% chance that some quantum phenomena occurs, you say, what happened to the other 10%? And the argument is, if there's an infinite number of Earths, that event occurred on 90% of them, and it doesn't occur on the other 10%. And all you're doing is finding out, which worlds you live on that are constantly unfolding in this way. Needless to say, physicists did not consider this helpful, this idea that there's an infinite number of parallel Earths out there. And this has been considered kind of the crazy aunt of quantum theory, locked up in the attic and ignored for a long time. until fairly recently, where certain physicists, primarily string theorists, have found that it's necessary to dust off this many worlds interpretation in order to make sense of certain aspects of their theories to develop a quantum theory of gravity. But it's tied into this notion of probabilities. It's an alternative way of trying to make sense of the probabilistic interpretation of quantum mechanics.
It's also why people think quantum physics is weird.
It is one of the many things. There's a lot of quantum physics. People think quantum physics is weird. But the fact that when you look at atoms, every atom has a unique fingerprint. If you excite an atom and give it a large amount of energy, when it relaxes back to a lower energy state, it doesn't give off light over the entire electromagnetic spectrum. It only gives off light at very particular wavelengths. And the set of wavelengths that are observed from carbon is different from that observed from neon, different than that observed from mercury. This had been known going back to the 1870s, 1880s. And classical electromagnetic theory is completely unable to account for this. And it wasn't until 1913 that Niels Bohr, developing the Bohr model of the atom, made the first, real attempt to try to understand this discrete spectrum of wavelengths given off by different atoms. The Bohr model is now understood to be not the correct explanation. The Schrödinger equation turns out to give the fully correct explanation. That you're going from 1870s to 1910 with this big mystery out there that physicists don't understand. And for those who attack the skeptic's point of view, those who say in issues of evolution and say, well, you can't explain this or you can't explain that. Yeah, scientists are never able to explain everything in the first place. And in the second place, sometimes it takes a while. I'm just glad that the physicists at the time didn't decide that this is the way atoms were designed. They didn't just say, why this specific, set of wavelengths of light? Shut up, that's why. But they kept trying to understand this, and their attempts to understand this led to the development of quantum mechanics, led to the cell phones and laptop computers and iPods that we use today.
And we'll be right back with more quantum mechanics with James Kakalios after these messages.
Skeptically Speaking wants you to question everything. To be a part of the discussion, call and record your question on our listener question line at Speak 73101. That's 773-257-3101. Long-distance charges may apply. Sunday nights at 6 Mountain Time, join our Ustream chat room to listen and ask questions as we record interviews live. Just click the Listen Online button at skepticallyspeaking.com. You can also email your questions and comments to live@skepticallyspeaking.com. Or if you're on Twitter, tweet us at Skeptical Radio. To find out where Skeptically Speaking airs near you, to listen to past episodes, or download the weekly podcast, check out our website at skepticallyspeaking.com. While you're there, follow the links to connect with us on our Facebook page, our Twitter feed, or to subscribe to the show in iTunes. And now, back to the show.
Welcome back to Skeptically Speaking. I'm your host, Desiree Schell, and today I'm talking to Professor James Kakalios about his book, The Amazing Story of Quantum Mechanics, a math-free exploration of the science that made our world. Now, a few episodes, we were talking about cold fusion. Now, you wrote that cold fusion would have to suspend or violate the principles of quantum mechanics to work at all. How so?
Well, first of all, fusion does exist. Nuclear fusion is a real physical phenomena. You take two protons and you can bring them so close together that the strong force will suddenly kick in. You can take four protons and through some reverse beta decay turn two of them into neutrons, and then you have two protons, two neutrons. You fuse them, you bring them so close together that they form a helium nucleus. And the helium nucleus actually has a slightly smaller mass than the separate two protons and two neutrons that you built them up out of. And that missing mass times c squared gives you a very large change in energy. So just that small change in mass can lead to a very large amount of energy. This goes on in the interior of the sun, where the pressures and temperatures are such that even though the protons are repelling each other very strongly through electrorepulsion, still a few times they can get close enough that a quantum mechanical process called tunneling will occur, and they can actually get so close that the strong force kicks in and holds them together into a nucleus, and you get fusion. Cold fusion says, yeah, I'd like to do that, but I'd hate to go to the center of the sun, even if you went at night when it's not as hot. And so what about if we could do this inside a metal? And there are certain metals like platinum and palladium that are very good at storing hydrogen atoms. And a hydrogen atom is basically a proton with an electron bound to it. And if I can put enough of these in the palladium, then some of them could get so close, if the density is so high, that they would fuse together and form a heavier nucleus, helium, and then they would give off a tremendous amount of energy. And so Pons and Fleischmann, these two chemists in Utah, ran this experiment. They claimed to be getting excess energy that was clearly a sign of fusion. The only problem was that there are like 6 other signs of fusion, and none of those were observed. And moreover, when they did a calibration check, which should have had no result, they got just as strong a result as before. And so there are all sorts of things that were crazy about this. Basically, the device should have given off a lethal dose of neutrons had it worked. So actually lucky for Pons and Fleischmann that they didn't actually achieve fusion, because otherwise they would have killed themselves. The other thing is that it would have required violations in the tunneling probabilities, that they should have had to basically wait millions and longer years for them to have seen anything to occur. So there's a lot of things that are just too sketchy about this. Every now and then we see something that we thought was quote-unquote impossible, showing that nature can still surprise us. But whenever you see some event that requires at least 2 or 3 impossible things to happen, then you got to be a little bit suspicious.
We have a question from email from Les.
Could quantum mechanics be used in the health industry, or other industries for that matter, like water, wastewater treatment, or firefighting? And how?
One way that it's being used is in the field of nanotechnology. We have gotten to the extent we're making these transistors and these devices smaller and smaller. And I mentioned that this quantum mechanical wave function is actually very small. In some cases, it can be about the size of an atom. In certain situations, you might be able to make it so that it might be the size of, like, say, 10 atoms. Well, we can actually now make devices that are only 10 atoms at a side, in any given length. These devices might have 1,000 atoms, 10 atoms by 10 atoms by 10 atoms, but the wave functions know that they're in this little quantum mechanical box. And this is the field of nanotechnology. This is the whole interest in nanotechnology, because when you put objects in these small boxes, you can change the properties from compared to when they were in a bulk solid. People are working on nanopharmaceutical drug delivery systems. They are working on developing, using nanotechnology and using the principles of quantum mechanics to develop drugs that they can be brought into a person and deliver the drugs only where the drugs are needed, so that you can have binding of certain chemicals to the tumorous cells, and that they will not bind and thus ignore the healthy cells. If this can really be developed, when you think about the efficiency of chemotherapy treatments for cancer, and to be able to target just the tumor and nothing else in the body, that would be huge. And of course, there are areas in health treatment such as I say, magnetic resonance imaging. This is an application of quantum mechanics that is now commonplace, but really it started where people just were looking at polarization of nuclei in the laboratory of individual nuclei, and eventually it developed into a technique that could be used as a medical diagnostic. There are devices called functional magnetic resonance imaging, where people have made small little sensors that they could put on the person's head and sense where is the oxygen flowing, which is a sign of where you're doing your heavy thinking. So they can actually watch people as they're thinking about trying to solve a math problem or trying to think about what to have for dinner, and they can actually see which portions of the brain are lighting up even deeper into the brain than just on the surface. So there's a lot of areas where quantum mechanics really is coming into the fore, from drug delivery to the diagnostics and MRI to even being able to sense what people are thinking about.
And one last question from Brent.
Do you think we will ever find the Higgs boson? What if we don't?
Unfortunately for physics, I think we will find it. I think that the Large Hadron Collider is got the best chance of finding it, and that it will probably come, if not in this set of data that has been acquired or is being acquired, then in the next round when they fire up the accelerator again. And I say unfortunately because it would fit all the predictions. It's the last piece that's missing in the puzzle of what's called the standard model. You snap that last piece into place and you've completed the puzzle and you've got the picture. But then once you've completed your puzzle, aside from maybe framing it and putting it up on the wall, you've completed your puzzle. If the Higgs boson is not there, if it doesn't exist where they believe it's going to exist, if you could show that there were no Higgs boson, well, everything gets thrown out the window. And if everything gets thrown out the window, then we get to re-examine a lot of the stuff that we thought we knew, and things become very interesting and very exciting. So this is actually not my field of physics. I work in solid-state physics. I'm not a particle physicist. But I believe that the Higgs boson will probably be discovered, but in some sense, if that's all they find from the Large Hadron Collider, then unfortunately that branch becomes mature. And we all know from our adolescence that once you get to maturity, the exciting stuff starts to go away. No, but once you've got things figured out, then you move on to the next terrain of what's next.
Oh, well,
what's
I have the next terrain. Teleportation. Now, I know I said I was not going to ask any more questions, but I really have to ask this question because you're right here. Now, I have heard that teleportation defies the laws of physics. So is that regular physics or quantum physics? Because I need to know who to blame.
Well, people do talk about teleportation in terms of quantum physics, but what they are basically teleporting is information. They have a prepared quantum state. They can separate two pieces of it from very far away, and it turns out that a measurement at one end of that quantum wave function can determine what gets recorded or observed at the other end. And so in some sense, information is being teleported over great distances. But it is not physical objects. It is not actual matter that is being moved from one location to another. So unfortunately, we're going to have to deal with rush hour for quite a length of time to come as far as that goes. But there will always be, even if the Higgs boson is the only thing that's discovered and that's it, and that part of particle physics gets, nailed down, and that is, of course, a tremendous achievement, there's always the next level of questions. There's always something else that we don't understand. And so this is never going to be over. We're never going to be done. I like to view it as job security. That there will always be problems and questions to ask, and that's what is so much fun.
James, you are lovely. Thanks very much for being here.
Oh, thank you very much for having me.
You can find links to James Kakalios and his book, The Amazing Story of Quantum Mechanics, a math-free exploration of the science that made our world, on our website at skepticallyspeaking.com. And we'll be right back to talk with Victor Stenger about quantum misappropriations, otherwise known as That's Not Quantum Physics, after this.
On the next episode of Skeptically Speaking, we're featuring an interview on the work of Dr. Elizabeth Loftus, author, university professor, and pioneering researcher into the ways our brains store and recall memories. And we're joined by Iowa State University researcher Gary Wells to discuss his new study on the ways that the administration of photo lineups can affect the memories of witnesses. That's next week on Skeptically Speaking, on your local radio station, or online at skepticallyspeaking.com.
I'm here with Victor J. Stenger, adjunct professor of philosophy at the University of Colorado and professor emeritus of physics and astronomy at the University of Hawaii. He's the author of Quantum Gods, The Comprehensible Cosmos, and the New York Times bestseller, God, the Failed Hypothesis. Welcome to Skeptically Speaking, Vic.
Well, thanks for having me.
Now, we've just interviewed Jim Kakalios about his book, The Amazing Story of Quantum Mechanics. So we've had a crash course in how so much of our technological society is built on discoveries in quantum physics. But unfortunately, there's a bit of a dark side to this story. And that comes in the form of quantum physics jargon being misapplied to, let's say, support less than plausible claims. So first off, let's talk about the most abused bit. The fact that a particle exists in sort of an undefined state until someone observes it. Maybe if you could just explain why that's only true on a quantum level.
Well, I don't think it's true. I mean, everything that we do is based on observation, so it's certainly true that a quantity such as a particle's position it can't be known until we measure it. But that doesn't mean it doesn't exist. There must be some reality out there, and we may not know exactly what that reality is. But that doesn't mean that we're making it just by making a measurement.
So when Deepak Chopra, let's say, when he says the moon doesn't exist until someone's looking at it, how off is he? Is he just a little off, or is he completely wrong?
Well, let me try to explain a little bit more background here, where this idea comes from. Because once again, I want to say that I don't know what reality is. Nobody can know what reality is. All we know is what we observe. And we describe what we observe in terms of our scientific models, and that's the best we can say. And there's no basis for assuming that what we observe exists in one-to-one correspondence with what's really out there. But again, that doesn't mean that we are in any sense creating reality with our own consciousness. And let me tell you how this idea came along and why it's so wrong. Way back from the beginning of quantum mechanics, there was this notion called the wave-particle duality. And what it basically said was that whether or not an object was a wave or a particle seemed to depend on what you decided to measure. If you were going to measure a wave-like property, then it was a wave. If you were going to measure a particle-like property, then it was a particle. And so it seemed like you were deciding whether the thing was a particle or a wave. But in fact, that was a total misunderstanding of what goes on. First of all, you always measure particle. And there's a classic experiment called the double slit experiment, where it goes back actually to Thomas Young around the year 1800, which was used to first demonstrate the wave nature of light. And early in the 20th century, it was found that not only was light particle-like, it had particle properties. It bounced around like particles do, and photons are the particles of light. But that things that we're accustomed to calling particles, like electrons, actually do produce this diffraction pattern from the double slit experiment. And so the idea came along that, sometimes an object is a particle, and sometimes it's a wave. Well, in fact, if you do that double slit experiment with very accurate detectors that could detect individual photons, let's say you do it with light, you will measure individual particles and not waves. You never measure a wave individually. The individual particles are still localized in space. And what happens when you do the experiment is you build up statistics with these individual particle hits, and eventually the pattern of those particle hits takes on this interference pattern that we associate with waves. Okay, it's a long story, I realize that. But the point is that the wave nature that we're seeing is not associated with any individual particle. It is associated with the statistical distribution of a large number of particles.
So then this actually leads to another common misunderstanding. The observer doesn't necessarily have to be a person, right?
Oh, sure. I mean, I can imagine a computer setting up the experiment and deciding whether or not to measure a particle property or a wave property, and then instead of sending that data to a human being, put it in a time capsule. And 1,000 years later, somebody opens up the time capsule, and so finally some human consciousness observes the result, and that's supposed to somehow reflect back 1,000 years and change the nature of that particle?
So what do you think Deepak Chopra is talking about then?
Well, he's trying to tell us that that consciousness has a direct connection to reality, that human consciousness is something beyond particles, beyond matter. And out there is this cosmic consciousness that we tune into, and we can affect, we can control it, we're all part of it. It's kind of a holistic thing. We're not individuals, we're all part of some great cosmic whole. And of course, that's a very appealing idea that has absolutely no basis in science.
Well, actually, another appealing idea is the idea that in a probabilistic universe, that just thinking about something can make it happen. And we see that in books like The Secret. So can you explain the basics for sort of where people get the idea that that is somehow quantum?
It is true that the quantum behavior is kind of weird based on our own common sense experience. And that's because we're not tiny little objects ourselves. We're made up of large numbers of particles, and the behavior that we observe around us is all pretty well described by classical Newtonian physics. And incidentally, that also involves the brain. The brain is really quite well described by Newtonian physics because it's too hot, the particles are too big, the distances are too large for quantum effects to play any significant role. But in the book like The Secret, they're again claiming that based on this notion of human consciousness being able to affect reality, that you can make yourself beautiful, you can be smart, you can be healthy. All you have to do is think it. And of course, while they claim this was some new discovery, the authors of that book, you have to give Chopra credit because he was saying that 20 years ago. So, but he was wrong then, and this current author is wrong now. They don't have any evidence for that, but that's the claim that's made, that somehow the brain is a quantum device, and it would be fine if you could show some evidence for it. I don't have a closed mind to that. If you showed evidence, and I've looked at the evidence. The book I wrote back in 1990 was called Physics and Psychics, where I tried to examine the evidence from a physicist standpoint for psychic phenomena, and that was the first time I started talking about quantum mechanics and psychic phenomena. And it's just not there. You can't point to a single controlled experiment that has been replicated that shows any such connection.
You're listening to Skeptically Speaking, and I'm talking to physicist and author Vic Stenger. And we're talking about the ways that quantum physics terms are misused in the service of pseudoscience. Another concept that kind of portrays the brain as being able to manipulate reality is something that they call quantum jumping. Can you tell us how that supposedly works?
Yeah, that's sort of part of the same story. The way quantum mechanics was originally formulated made it seem as if, again, the conscious brain was causing a wave function. The wave function is the way we describe quantum phenomena, is a mathematical function that is used to calculate the probability of something happening. And when you made a measurement, the way the original theory was formulated, it caused the wave function collapsed. It's called collapsed. And Einstein, way back in 1923 or something like that, I think it was, a big conference in Brussels, first so-called Solvay conference in Brussels, in which every famous physicist of the time was present. In fact, if you look it up on the web, you'll see a wonderful photo of all these great physicists assembled at the hotel in Brussels. And all these physicists got together to try to figure out what quantum mechanics was all about. And they talked about this wave function collapse thing. And Einstein just spoke up and said that it was spooky. He just couldn't believe it. Because what it implied was that when you made a measurement, when you made an observation, then all over the universe, you sent some kind of signal out from your brain to cause this wave function to collapse all over the universe, because the wave function gives you the probability of finding a particle that you're observing at any particular point. And before you make any measurement of that particle, you don't know where the wave function is, which means it could be any place in the universe, and so the wave function has some value all over the universe. And then you make the measurement, and it collapses instantaneously all over the universe. And that seemed very weird to Einstein, and he called it spooky action at a distance. And the point was that it wasn't a real thing that you were measuring. You weren't measuring the wave function. The wave function is just a mathematical object that is used to describe the phenomenon. And it's not a real field, a wave that's out there all over the universe that you are then just collapsing when you think about it. And that's, again, the gross misunderstanding of what quantum mechanics is all about.
Well, how about something like quantum touch? As far as I can tell, that's sometimes known as therapeutic touch. And while basic human touch has been shown to be, valuable in many different circumstances, is there anything to the quantum bit? Or have they just tacked that on at the end to make it sound more sciencey?
Is something I actually am quite familiar with. In fact, it was debunked back around 20 years ago or so by an 11-year-old girl, Emily Rosa, whom I know. At the time, she was living not too far from where I lived. I knew her and her family. And it doesn't even involve touch. The idea is you just kind of wave your hands over a person, and you can adjust the bioenergetic field that supposedly surrounds them. Again, I've written a number of things on that where I point out that, again, you can't find a single piece of evidence to support the notion that that the human being or any living thing possesses some kind of special living force that surrounds them. Now, this is a common belief that we have this aura and so on, and it's often associated, incidentally, with electromagnetic waves. So we can detect electromagnetic waves down to a very low level, and the body does have some emission of electromagnetic waves. First of all, we're a heated body. We're not at absolute zero temperature, so we emit what's called black body radiation. It's not in the visible region of the spectrum, it's in the infrared region. It's no different for a living body than it is for a rock. The rock at the same temperature as a human body would emit the exact same radiation. So it's nothing to do with life. Similarly, there's no, our hearts emit and brains emit electromagnetic waves, very weak ones, and they can be detected. But that's just due to the electrons jiggling around in our hearts and brains, and it's not, again, anything non-physical. It's nothing that we don't understand and haven't understood for 100 years.
So then why do you think that the concepts in quantum physics are so attractive to people who want to make their ideas sound like science?
Well, they can make money at it. You look at the internet, you search up quantum healing, and you'll see thousands and thousands of entries of people trying to sell you their product because people aren't satisfied that medical science can make them live forever, and of course it can't. Part of the problem is that they're being exploited and always have been exploited with the promise of rewards for which we have really no hope whatsoever.
Well, is there any less malicious reason, though? Because there are people who genuinely just don't understand quantum physics, and I will put myself in that category. I absolutely do not. Maybe I should ask, is there any way for those of us who haven't spent 40 years on physics research to tell when someone is abusing the ideas of quantum physics? Are there any obvious red flags?
If they're telling you that if you send me some money, I can help you solve your problems, whether they be mental or physical, that's a red flag right off the bat. Or you buy my book and I'll solve all your problems for you. This book is going to do everything, and so you'd have to look at the claim. If the claim, the more outlandish the claim is, the more likely it is to be phony. It's a very simple rule to make. You have to, I think, just trust the majority of scientists. When 99% of scientists say something is likely to be the case, and you shouldn't follow the 1% who tell you something different that is more along the lines of what you want to be true. You have to trust it, or you have to learn science yourself. That's the best way.
Well put, sir. And thanks very much for being here, Vic.
Thank you. Thanks for having me.
You can find links to more information about Victor Stenger and his books on our website at skepticallyspeaking.com. And while you're there, click the links to Facebook, to Twitter, or to iTunes, where you can download this episode, subscribe to the show, or leave a review. Thanks for listening, and we'll see you next week on Skeptically Speaking.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Shell gonna raise a little hell, metaphorically that is. 'Cause we're skeptically speaking.